Welcome back. Now we're going to look at 2D examples of center and mass calculations. Okay, we're going to compare the centroid and center of mass of the upper unit semi-disk, so basically bounded by the upper semicircle, with density x squared, square root of x squared plus y squared, which of course is the radius r. Okay, so similar to our bent wire example, we have a semicircle to work with, but now we're looking at all the area underneath it and finding the center of mass. Again, our x average will be 0 due to symmetry geometrically. And if we look at our density function and evaluate it on a positive x and a negative x getting the same values, we know that our x bar is also equal to 0, since rho of negative x, y, equals rho of x, y. It is symmetric, as an even symmetry on both sides. If the density is constant in a certain direction, that's also even. The density changing, if you change the x to a negative x and the density function does not change, that means you have even symmetry in that direction or across the perpendicular axis. Y average, not so much. Even though the density function is even in the y direction, the geometry of the shape does not have an obvious center. Let's first look at the area, which is pi divided by 2. The area of a circle is pi r squared, so the area of this area inside the circle is pi r squared, so half of that is pi over 2 for our radius of 1. Let's combine that together for y average. We are looking at nice polar limits. Set up our integral very similar to what we had in one dimension. That arc, that bent wire. You'll see very similar integrals, what we just had before. This is 2 minus a negative 1 plus 1. And this one is 1/3 the value. So we get 2 pi times 2 times 1/3 gives us 4 over 3 pi. That's our y average. 4 over 3 pi is approximately 4 over 9. So thinking about that is a little bit bigger than 1/3. Now let's look at how the integral changes with the center of mass, adding in this density function. I'll write down x average, y average equals 0 and 4 divided by 3 pi. Since we'll be doing the same limits, let me first calculate mass. Of my density function, r, my Jacobian, r, dr, d theta. Here I can factor out a pi based upon the integral term of theta. Integrate r squared, giving me r cubed over 3, and that gives me pi over 3 is my mass. Now I'm going to erase a little bit and calculate y bar up here, or I should say m y bar. Before I erase this chunk, I'm going to set up my limits again. Oh, they're the same limits here. Never mind. I'll erase it. Plug in my y. Jacobian, pay the cost. Try that again. So m y bar, I first plug in my y. Then I plug in my density function. Then I plug in my Jacobian, dr d theta. So let's break that up a little bit. This is y, density function, and then this is Jacobian. So it's good to keep track of all the pieces that we're working with. Similar integrals. This will give us minus -1 plus 1. That's 2, giving times 1/4 minus 0. So we get 1/2 for this moment. And we combine our mass we computed and the moment to get y bar equals over 2 pi. And if we combine that with what we know for x bar y bar is equal to 0 and 3 over 2 pi. again, we can approximate pi is around 3, so this is fairly close to 1/2. And since we're dividing by just a little bit more, it's a little bit less than 1/2. So the centroid ended up being 4/3 pi, just a little bit above 1/3. And the center of mass ended up being 3/2 pi, just below 1/2, with 0 values in x. So there we go. So working from our centroid, the geometric center, and then applying this density function where the density increased with distance, our center of mass moved outward radially. Because our density basically is going from 0 right here up to 1 up there. And so the centroid gets moved out. Okay. So there's our comparison of the two. I graphed my approximations. You could use a calculator if you're less sure about approximating in your head. But again, we're just looking for a visual comparison. Which one's higher, which one's lower, how close are they? And then once you have that, it's good to reason out why. Why did the density function given to you affect it in this way? Is that expected? Did you expect that change? Building your intuition. Now, move on to another example that is a little bit different, but gives us a chance to also work in 2 dimensions. This one's a little bit different. We're asked to evaluate an integral, double integral. We have no information, but it happens to be in the section on center of mass. So first, can we integrate directly? No, because we have that e to the negative y squared dy. Now we've seen this function before. We used polar coordinates to be able to reorient it. But in this case, we already have an x. So it's a little awkward to reorganize in polar. Let's just try to change the limits of integration on this to see if it's a little bit more clear and draw the region that we're integrating over. With the limit of square root of 1 minus x squared, we know we're working with circles. We have an upper semicircle, just like before, and x is going from -1 to 1. So we know that we're integrating over the same upper semidisk. Now what we have is an integral of x times e to the negative y squared. So what we can do is think of this as a double integral over a region of x times some density function of x and y, dA. So this is the x moment, or say m sub y-axis. And this density function is even in the x direction, because the density function is e to the negative y squared. It doesn't change. It's actually constant. So we can think of this in the x direction as having a constant density. And so we look at our shape. It has symmetric limits, or the geometry is symmetric about the y-axis in the x direction. And so we know that by symmetry, x bar equals 0. So the moment mx bar must be equal to 0. So without any integration, we know that this equals 0. So thus, the integral given is 0. Now, you can actually calculate this by integrating out, and not in terms of y, but in terms of x. If you change the order of integration, you would get limits and be able to integrate in terms of x first and verify that the integral, when calculated iteratively, is 0. But I want you to think about some of these integrals we run across as being of the form of a mass integral, a center of mass, or a moment. So if we identify an x times some more complicated function, think about that function as a density function. Does it have certain properties? Is it symmetric in the x direction? Can we use symmetry? Does the shape have some symmetry that we can work with? It doesn't in the y direction, but it does in the x. So, one example to think back and review on our more complicated integrals and ways of immediately evaluating them. For this last example, in 2 dimensions, we're going to look at something that's a little bit different. We're going to go back to the discrete idea of adding up little chunks of pieces and compare that to a more continuous center. So in this idea, we're looking at discrete points, in this case, populations of counts that have been made to track cases of an outbreak within a city. This is almost too relevant right now, but it is a model that's used to find the center of a spread of something. In this case, we're looking at the spread of a disease with some center within a city. This was used in the province of Wuhan, the city where COVID-19 had the first outbreak, and it was used to identify approximately where in the main city the first infections happened, and then following up by word of mouth, asking where people had been, finding common locations. They were able to track the initial exposure to an outdoor food market. And that idea is combining both combinations of data analysis, which we are touching on right now with our integration, and following up using survey data, information from people. So I just want to touch on that because it's something that is very relevant to what we're doing, but is different than the algebraic integration techniques we've used so far. To rethink of this in terms of what we've done so far, we again think of the moments, mx bar, and the mass m. But in our case, the mass m will be the total population of cases. The total population of cases. And our mx bar will be the weighted amounts of cases by their distances. So you can think of this as the sum of the populations at each distinct point times their x value. So we'll think of that as x sub I times the population sub I, all added together. And in the same way, the y bar will be the summation of y sub I times the population amount divided by the total population. And to do this effectively, I'm going to create a table of these values. First, labeling the points or locations then the population sub I, number of cases, then weighting xi population sub I, yi population sub I, and then adding up these pieces. So I'll just start from the far right and then move across the board. I have 2, 0, then 1, -1, 0, 1, -1, 1, and then up top 0, 2. And I'm going to label the populations of cases at those points. So 10, 30, 30, 20, and 10, and then scale each location coordinate by the population. So xi are all the x's times that y, all the y's times it, and these will scale pretty nicely here. Get 20 and 0, 30, -30, 0, 30, -20, 20, and 0, 20. And now, when we add up, we tally these pieces, we're going to get our total, our moment mx bar, and our moment my bar. Put it right there. So the total, adding up, we get for 100. 100. Mx bar, we get 20 minus 20, that's just 30. And then this is not right. That should be 1, +1. Apologize there. That's 1, 1 for this location right there. -1, 1 is the 120. Okay, that's a good catch there. Whew. 60, 80, 100. So now that we have added up our total population and moments, total moments, then we know that x bar and y bar are 30 over 100 and 100 over 100, which can be simplified to 0.3 and 1. These are the population. It's the population center of mass, or population center. Now let's graph where that is. 0.3 and 1, well, 1's right here, 0.3 is right about here, so makes sense. It's right where the highest counts were, and that's where we would start anyways. So there's our population center. How does that compare to the geometric center? Well, it often makes sense to go to the heart of the city, or the center of the city in this case, to start out. And in that case, we'd have the centroid, or geometric center of mass, compared to our center of mass. Our centroid was what we calculated last time. This time it'll be scaled by 2 there. And so you could see the centroid is a good place to start, but the data tells us, but following the data tells us a better balance point over that region. Okay, that ends our look at two-dimensional problems.